Okay.
Okay, go.
Last week we had an alum back. His name was Hisham. You didn't know Hisham. Hisham Hoffman. He was a high student in 1986. But this year we have a young girl alum back here. Those of you that have been here for a while might remember Pablo. If you've been here that long, there's a minor problem, but I'm sure you'll get over it. Pablo graduated in 2008 and came to us from Argentina and went from here to Boston. Started off at the Charles River Associates. Those of you that are not familiar with Boston, there is this river in Boston called the Charles River. And MIT is on one side of the river and Harvard is on the other side. I don't know, I don't go there very often. School. Okay. But Pablo now works for a bunch of different people. These are all the icons where he is being pulled from. But I would say Brattle Group. This is not Battle, this is Brattle. And that's a group that emerged from the Charles River people.
Started by an alum of University of Illinois.
Really? Who's that?
The chief guy.
Well, he was the second generation. So
No, he got his master's here. What's the name?
PhD, Peter Foster.
Peter
Oh,
Foster.
Peter Foster. Yeah. All right, enough of this stuff. But Pablo also works at a university called Tufts. So I don't know what's these two words, Brattle and Tufts. Makes you wonder what your kids are going to grow up thinking about. But Pablo's going to talk about something interesting. He always does. You don't need this, but welcome back, Pablo Ruiz. Who is like Alejandro, he can speak in at least 2 languages. And today's going to be in English.
That's right.
Okay.
Pablo studied Portuguese once when he was here.
That is true. But I will not do my technical Portuguese is not quite.
So you can talk Portuñol.
Okay, Pablo.
Thank you.
Thanks for coming.
Thank you. It's a pleasure to be here and spend the day, be with at the new building, and also talk a little bit about the research. Myself and my colleagues, there are many of them, as people are saying. I only work at Brattle and Boston University, but it's a large team, and I coordinate the effort, so I do get pulled by different people. This is a large effort, as I said, funded by RPI on topology control. The agenda for the talk is as follows. We'll first discuss what the objectives and motivation for changing the topology of exposition grid, or basically for opening and closing circuit breakers is. We'll provide an illustration of why that could work, why that could be a good idea. We'll talk about the current practice in terms of switching solutions, and then we'll go deeper into the project, the different approaches to conduct the optimization, and then we'll spend most of the time talking about 2 sets of simulation results on real historical data from PJM. PJM is a team member, by the way, in the project, on applications of topology control to relieve overloads, either in operations or operations planning conditions or settings, as well as to improve the market efficiency. So the goal of changing the topology of the transmission grid is to extract more value out of transmission facilities, either existing facilities or new facilities. And basically, this additional value comes from identifying additional operational controls to perform a series of things such as manage congestion, respond during contingencies, accumulate outage requests, and so on. Note that I'm saying identify rather than provide new controls. These controls are already available today to operators, except that it's very hard for them to know which ones are feasible, which ones are beneficial, since most of them are not. When one controls the topology of the transmission grid, the idea is to significantly lower generation costs, and we'll see results about that. Enable higher levels of variable renewable penetration, especially in cases when curtailments are due, or renewables curtailments, especially wind, are due to transmission constraints, and increase system reliability. The time frame of these decisions are from operations planning, so several months ahead, up to intraday or real time, just to give you a sense of what we're talking about. So to provide some motivation, let's take a look at in this slide and the next, a few screenshots from LMP prices, real-time LMP prices. These are peak conditions in 2013 in PJM. The deep reds, you may know the scale already. Deep reds are prices in the $1,000 per megawatt hour range. The blues are in the $10 to $20 per megawatt hour or so. So you see that these three come from the day that set the peak record in PJM. It was July 18th, 2013. Three snapshots come from three different times: 11:55 a.m., 12:20, and 3:30 p.m. You see that there are huge price gradients, and that they move around. And these price gradients, these congestion patterns, do not happen only during peak; they can happen at any point in time. I took a few snapshots from the MISO website a few weeks ago. The violet, or the purple colored regions have prices below minus $10 per megawatt hour. Again, the orange is in the $100, $200 per megawatt hour range. So congestion moves, as I said before. So wouldn't it be nice to be able to increase the transfer capability dynamically or adaptively as system conditions change, to be able to transfer more power out of low-cost units that are not fully utilized to the load centers? You can think of our goal as exactly that. So I'll illustrate how topology could work, the topology control could work with a very simple example. Many of you probably saw the 7-bus case from PowerWorld. I massaged it a little bit to create the congestion that I wanted to see. And so in this test system, you may recall that the unit in bus 2 is the lowest cost unit. Bus 4 is the most expensive unit, but still, even though there's plenty of additional not used capacity on bus 2, it cannot be fully utilized due to congestion in this particular case from bus 2 to 5 and 5 to 4. So the figure on the upper left-hand side shows exactly the same dispatch, but with the price contour. So we see that there is some flow that goes from the lowest cost unit, the bus 2, on both congested paths, and then to a different path. So that's a specific path that we can open by opening line from 4 to 3, or the breakers that are in series with that line. When we do that, basically all of the flow from that path, and as well from other paths, all of the flow that is used to serve the load in bus 3 remains on the left-hand side, reducing congestion and providing additional room to redispatch the system and providing some savings. So in this particular case, savings are $453. That is just for illustrative purposes. In the table, you can see how the low-cost unit of bus 2 increases the dispatch from 220 to 296. how we can shut down the unit, the most expensive unit in bus 4, after we optimize the configuration of the system to these system conditions.
It's interesting, because last week, Kishan Lupton stood up there and said, it's all about the money. So here we
So
are
there you
again.
go.
Here we are again.
Right. Yeah, so people can get very excited, and we'll see as the results we obtain simulating in detail the PJM models are very promising, providing savings of, in terms of the money, providing savings of the order of 50 to 60% of the cost of congestions in by providing that capability. So topology control works, and because it works, it's being used in a variety of applications today. It is being used for congestion planning, in outage coordination and scheduling, for congestion management. So the caveat is that all of these reconfigurations are identified manually by transmission engineers in the control room or operations planners outside of the control room. Having to spend a lot of time and definitely not coming up potentially with the best solutions. And so our goal is to provide some tools or develop the technology that, to provide these reconfigurations quickly enough, but to inform the operators of these additional decision variables that they can take. Now turning over to specifically to the project, the objective is to develop a full-scale algorithm that will work with the existing tools, the EMS, the MMS, contingency planning tools, outage management tools, and so on, while meeting computational efforts that are commensurate with the operational decision timeframes. So we need very fast solutions, meaning in the order of minutes. So what we're looking for is good solutions that can be obtained quickly, not necessarily the most optimal solutions at this point. While accounting for reliability, of course, and not just the standard reliability constraints, security constraints, some stability constraints and voltage criteria, but also some more topology specific constraints, such as connectivity constraints. When you open a branch, when you open a breaker, you cannot necessarily radialize load that wasn't radial before. So you need to be careful on those aspects. Aside from developing the algorithms, we spent a lot of time simulating what the impact would have been, and we'll go through some of those results next. The basic architecture of the technology is as you would have expected, most likely. So it's basically two main components: a component that performs an optimization over a reduced set of constraints, and another component that assesses the feasibility of the solution. And if it's a no pass, it feeds back additional constraints for use in optimization. So in the next couple of slides, we'll talk about a couple of the tools that we use on the optimization component. The first is a very simple sensitivity-based 3D type of algorithm, iterative algorithm, in which in step one, we select one or more candidates for opening or closing, basically for changing the state. Then we solve an OPF, see if things have improved and are feasible. If so, we keep them in and go back and look for more candidates. If not, we revert back. So very, very simple. Then we keep iterating until we run out of candidates or meet some other conversions criteria. For this particular very simple algorithm, one could use a variety of tools to identify good candidates. So one of them is the sensitivity of cost with respect to changes in line flow, which are very convenient because they are the difference, the partial derivative of the cost with respect to changes in line flow. Can be expressed as the price difference at the two terminal nodes of a given branch. So these are byproducts of an OPF. So in that sense, it's a very computationally efficient measure. One could interpret this particular sensitivity as the profit that the line would make if it was a financial entity buying power from the phone bus and selling power at the 2 bus per unit of flow. So under that representation, it becomes very clear that one would tend to try to disconnect lines that are not profitable, and would try to reconnect lines that one would expect to be profitable if connected. So this is one. There are some other sensitivities that one can use. It has very nice properties. The algorithm itself, it's feasible in each iteration by design, by construction. In this particular sensitivity would ensure that in the base case we do not island anything. It doesn't take care of the contingency connectivity constraints which come to enforce outside of the problem.
Pablo, what does the first bullet mean there?
The first bullet means the decision variables are integer variables. So the breakers either open or close.
Right. So how do we linearize that?
Right. So we take derivatives of the flow as if we could make a differential change in the flow. So as if we could force the flows to change. So that's what it means.
So do I assume I have an interval between 0 and 1 where I can vary it, or what?
Exactly. So you can take it that way.
Is that what it means?
Yes.
Okay.
So, but you arrange you order the lines based on the partial derivative, not the total cost that they would have.
So this is one approach. You can order them in any for example, using a total derivative, which is basically the vector product, the level ES times the shuttle cost of boundary constraints. You will get potentially a slightly different ordering, and then you use the ordering that you came up with in selecting these candidates. So this is one tool we use. Another tool is a reformulation of the mixed integer program for topology control. Just to by way of comparison, in this slide, I include the most widely used topology control formulation, which basically for the cases of contingencies would solve. This is a DC security constraint formulation. Would solve a full power flow for each contingency. The Z's are the 0, 1 variables for topology changes, and the T's are contingency indices. So in this particular formulation, the number of constraints are a function of the total number of transmission lines in the system times the number of contingencies plus 1, since you have a base case. This is very much intractable, and I'll show you a couple of results. And it's quite different from the usual DC security constraint OPF that is being used in the markets, which is based on sensitivities directly. The key here is that in the markets or in the control room, these problems are solved again and again. The topology doesn't change too much, so you can basically calculate the sensitivity matrix once and then keep iterating. This is a much more compact formulation. It's the number of constraints is basically the number of units and the number of monitor contingency pairs or transmission constraints explicitly, which is a much smaller set than the number of contingencies times the number of lines. So the question is how to incorporate topology control in this type of formulation, and we do so by using flow canceling transactions or virtual transactions that would emulate the outage of a line by adding additional sets of equations that will, for the lines that are open, will force the flow on the interface of the line and the system to be 0. And that constraint is a linear constraint. It's posed there for the case of multiple line openings. So we can go back to our to our sensitivity-based lip formulation and add a number of constraints, basically adding the impact of those virtual transactions on our original flows. If you go back. We add another term. These are the magnitudes of the virtual transactions, and then add a set of constraints that will ensure that if the lines are open, we meet this, which forces the flow at the interface of the line and system to be zero. If you have any questions, I'm sure that this has been discussed at length in some of the graduate courses here. So some numerical tests. So we got data from PJM. In this particular case, we looked at a snapshot from the PJM state estimator. It happened to be June 23rd, 2010 at 8:30 a.m. There were 156 base case transmission constraints and 30 contingency constraints.
What do you define as a base case transmission constraint?
It's a constraint on a line flow, transformer flow for no contingency.
They were operating like that?
Some.
You mean it was at a limit?
Well, so these are not necessarily binding, but about, I would say, one constraint every 10 are base case constraints. They tend to not be the most binding ones. And this is just an illustration of it. We have 20 switchable lines for this particular snapshot, 20 scenarios just to provide some variability for more representative results. And we set the time limit to 1 hour. So in the table below, and focus on the case split contingencies, which is the more interesting one. If we solve the more compact formulation, again, for the 20 switchable lines and the 20 contingencies with 30 post-contingency constraints, the solution varies between 9 seconds and 5 seconds, with an average of about 7 seconds over the 20 samples.
What are those numbers? What are the units there?
The units are seconds. Solution
For everything?
Yes. So all the units are seconds.
So I don't understand average, and then you have those different numbers. What does that mean?
So in the case with contingencies, the B theta formulation and we try with two different types of solution approaches for the LP, dual simplex and barrier. For the shift factor formulation, for the more sensitivity-based formulation, we just use dual simplex. So what these numbers mean is, so this is the average time over the 20 scenarios that it took to solve the optimization problem. So with the larger formulation, it takes a lot longer. So about over 2 orders of magnitude longer. And usually it doesn't converge. So you see that we are stopping right after the 1 hour limit.
And so where is the psi formulation?
Psi formulation is the formulation I just went over, basically a shift factor based formulation in which we model changes in topology by superimposing virtual transactions or flow canceling transactions rather than explicitly model the change in impedances or admittances, as is the
The
case.
secret Bradley method.
Sorry?
The secret that Bradley method.
There you go. This is not an approximation. This is exact for the DC. This is the solution.
The DC is an approximation. So when you say exact DC, it's an exact approximation?
It's an exact approximation.
Yeah.
So the solution.
Okay, so I mean, if that
So the
makes sense
solution-
to you, then I'm okay. It doesn't make sense to me.
So the solution of this formulation and the other one, which was also formulated in terms of DC, they are the same, provided you converge on the other one.
Yeah, I was just wondering, like, if we discussed earlier, if there's a two-line outage, then that is the same transaction that we use for cancellation, even know if it's like multiple line outage. It doesn't matter, like,
Right,
are there
so-
simultaneous outages or not?
So these are multiple changes in topology, and the condition. So these are all matrices, and the flow canceling transactions is basically a vector of.
So you're choosing one scenario out of, like every scenario corresponds to multiple line outages.
Well, or basically for any z, for any state of the system, the v's, the flow canceling transactions, will provide an exact representation of the outage of those of the vector z. One could use the same trick of superimposing the virtual transactions on other models, even AC, and then there's another definition. Any other questions on the optimization approach? The rest of the slides are about results. So the first set of results are.
Can you tell us, before you move on to examples, what is your contribution here?
So both of the methods are our contribution.
Or what?
The two optimization methods that I presented are our contribution through the project.
So nobody used DC approximation, or what is the?
It's clearly it's not the DC approximation, but it's the way we formulate the problem in a way that you can handle.
Well, I see it's privileged and confidential. I didn't know which part of this formulation is privileged, and then which one is confidential.
I forgot to remove the privilege and confidential. Being in consulting, you always start from the template, and then you forget to do this thing. So in terms of overload relief under historical cases, we looked at one case, the same case for which we saw the LNP contours from July 2013. And this particular day, in the afternoon, you remember there were very deep red prices around the First Energy Northern Ohio area. It's exactly that area. So this is an indication of the at-sea interface. This interface was being overloaded. There was a transformer Tom being overloaded, and in this case, 345 to 765 kV transformer. And this was after PJM operations deploying about 2,000 megawatts of demand response. So this was a base case overload, mild, but still a very large concern. That happened because there were a variety of transmission, unexpected transmission and generation outages going on, and the load was very, very high. At the same time, there were also post-contingency overloads in the 138 kV system. So we took the snapshot from a series of snapshots from the state estimator that included all of those conditions. We froze everything except for the topology. The reason is, under such challenging operational conditions, it's very hard to know what is really feasible and what is really not. So just to be on the conservative side, we fixed everything except for the breaker status, and worked to relieve, or let our algorithms try to relieve the overloads without, both under the base case overloads and simultaneously the post-contingency overloads, without leading to additional overloads. And these we were successful. In fact, it took about switching out 8 transmission facilities in the neighborhood, 3 of which were 345 kV branches or transformers, and 5 at 138 kV. 138 kV level.
But you didn't consider if you could do it with generation?
We didn't consider because, so for 2 reasons. One is PJM reviewed all the results. And once you start optimizing topology and dispatch, it gets very tricky to interpret the results, since basically what happens, congestion or overloads end up moving around.
But you could have done a simulation to see.
Yes. Well, so the next set of results which focus on the market, then we optimize. In this particular case, we wanted to be very graphic and descriptive to PJM operations. Any questions on?
But you could sort of find the value of the topology control if you did that.
Right.
So, where, just in general, are the branches that I shown on it when you switched out?
So that's one of them. So you look for the green boxes.
These are power world
These are
breakers.
power wall breakers, which we. One of the lessons, one of the many lessons I've learned from Professor Gross was that dealing with real data is messy. These are snapshots from the state estimator. The numbering convention changes for every snapshot. What is it from? The two bus, the limits change, many things change. So what we try to do here is provide a mapping, an approximate mapping of where the different facilities were. So that's why you see some gaps that most likely are not so bad.
Well, yeah, just curious, who does Canton?
So this is just a depiction of what the LNP interpretation of overloads would have been. We were not, since we froze the dispatch, these are not LNPs. And we're trying to visualize also if there is any price gradient in these contours, then there are overloads. So the second set of, and I would say more representative set of simulations are based on one operational power flow snapshot from the state estimator from four representative weeks, 3 average weeks in PJM 2010, and the summer peak week that I mentioned before. We took a lot of different types of data directly from the power flow, the starting transmission topology, branch parameters, unit commitment dispatch, interchange, status of shunt devices, and the initial voltage state. We got data from the real-time market, generation bits and constraints, as well as transmission constraints. And developed the models, making a few assumptions. I will not go into them, I don't think they are as important. Well, except for this network service requirement, that is basically a set of connectivity constraints that require that any load or generator connected by more than 2 branches remains so after changing the topology. The models are pretty large, up to 15,000 nodes or so, with 650 dispatchable thermal units. We fixed everything outside of PJM to whatever, to what it was in the historical cases. 4,700 monitor branches, about 6,000 contingencies, same list of contingencies that PJM uses to work with. The economic performance or the value of topology control, as previously was saying. We measure by taking differences in production cost with transmission constraints or with topology control minus the opposite. Production cost without topology control or the historical case minus the production cost with topology control as compared with the total cost of congestion, which is defined as the cost with transmission constraints in the base case or the historical case minus the production cost if there were no transmission constraints altogether. That's just to provide a benchmark on the savings. That is different from the market, that is different from the congestion rate. It could be different by about an order of magnitude, just to clarify. So the impact of topology control on PJM real-time markets, the market cost savings are in excess of 50% of the cost of congestion. which under 2010 conditions translate to about over $100 million. And these are based on the weekly simulations, basically assuming that the summer week is representative for the entire season, the winter week is representative for the entire season, the shoulder are representative for both spring and fall conditions.
The production cost without transmission constraints, does it include contingency cases?
Yes, we remove all, we leave losses in, but remove all of the transmission limitations, both base case and post contingency.
When you say base case,
Yeah, base case is not,
does
no
it
contingency.
include that? I'm trying to understand if all the contingencies are accounted for in cost of congestion.
Yes. So the case without transmission constraints has no contingencies. With no transmission constraints whatsoever, including contingency constraints. The original case has contingency constraints.
Can you figure out who lost the $100 million?
So I don't know who lost it, but clearly Illinois profited. That's a good thing.
It would only be parts of Illinois,
Possibly.
okay, not all of Illinois.
The PJM part of Illinois. So these are non-trivial savings, and basically they are enabled by additional transfers. The weekly changes in transfers between PJM regions are indicated here. So an additional 7% of energy exports from ComEd into the rest of PJM, an additional 28% of exports along the AEP Ukraine border into Allegheny and Pennsylvania. Additional 14% of imports from Dominion, and additional 5% of export into Eastern PJM. So basically what it implies is that there is a price smoothing effect also. The estimated change in average real-time LMPs or real-time load payments will be about $2 billion or so. Those are not real savings, and that's why I don't have them in the slides, since most likely they will be at least partially compensated by potential additional capacity payments and so on. But these are not minor changes.
But doesn't this affect the FTRs and stuff where people, it's like insurance, right?
Yes. So we're analyzing that problem right now, and that's basically what gets people in arms every time.
Yeah.
Now, what's interesting is the feedback we got from FTR traders is that sometimes they would prefer this type of approach to the more chaotic, ad hoc, operator-based intervention on the topology. So at least they will know what's going on. But yeah, it will definitely impact FTRs. The savings are enabled by breaker operations, and most of them are under 200 kV, so most of them are at the 138 kV level. About 20% of this particular week are breakers at 230 kV level. The algorithms did select some very extra high voltage facilities for removal. The green is 765 kV. This happens late at night and only for a few hours, and then they are connected back to maintain reliability. In terms of number of operations or number of breakers being open or closed, they are in the very few per hour. By the way, this is much less. So in the case of breaker switch close, a median of, for the summer peak week, a median of 1 breaker per hour across the week. The median for switching open was 0, but you get the picture of that the number of operations was pretty small, especially compared with the number of outages that were going on, or actually that are being requested all the time. Most of the breakers that are being opened, most of the facilities that are removed from service, carry relatively little flow. On average, 40% or less. In the case of 230 kV facilities, so slightly over 40%. In the very high voltage facilities, in the order of 10 to 15%, which indicates why removing them from service will still not cause reliability issues, but potentially relieve reliability issues. It also is good from a maintenance perspective. The lower the flow on the breaker, the less stress the breaker has.
Well, but every time you open up a line, too, you stress the generators because the shaft torque.
Right, but because the changes are pretty small.
Right.
This is nothing compared to opening a short circuit, a breaker under short circuit.
So someone could determine the shaft torque created by every switch and then compute the change in lifetime of the generator.
That may be about $100 million.
That's a transfer of wealth from generator to transmission.
Well, it's like the 60-degree, if you have an open breaker
Right.
with a 60-degree phase angle across it, you're not allowed to close it because of the torque that it creates on the generator.
Right.
So
I think that's a good point, and we could record the delta angle when we are closing.
Yeah.
This is basically an indication, because the flow is relatively low compared to the normal rating, not the short circuit rating, but the normal rating.
So you didn't check the angles before you closed them?
Not the angles, because we didn't have a constraint on the angles.
Oh, you're flying by the seat of your pants. Interesting.
So to conclude, most system operators today employ transmission reconfiguration on an ad hoc basis using the operator's previous experience. What we're working to provide is practical technology to enable a transparent use of topology control, transparent and consistent, with significant efficiency and reliability gains. And we can obtain solutions within a few minutes. They have been very effective in relieving historical overloads as well as historical congestion in the real-time markets. And we are right now working on the optimization of topology and unit commitment. That's a much harder problem. Two sets of discrete variables, as well as looking into the FTR market impact.
Does your company now own also Tabors, Karamanis and Associates?
No, they are independent.
Really? Because I thought that's why you called it TCA.
Right. That was topology control angle. But it's, so their logo used to be blue, ours is green because we are enabling higher levels of renewable energy.
Any questions for Pablo? Oh.
So I find this stuff really interesting. I'm working on geomagnetically induced currents, and a really big topic in that is how to mitigate the effects of geomagnetically induced currents. And like the currents are induced into the lines themselves, and so something I've been playing around with recently is doing topology control to mitigate the effects of it totally. And I was wondering if you had ever seen that in any of the literature or anything that you were looking into.
I haven't.
Isn't that opening the neutral? Isn't that one of the options?
Yeah, so if you
He's looking at opening the line.
Yeah, so a big
Different than
mitigation thing is to put like a blocking device in the transformer itself, but like using topology changes could be really good because it doesn't require any extra hardware installation or anything.
Right.
And so I found this really interesting, and it could be a potential application.
So, a couple of quick questions. talk, I think I have a better intuition the goal of the topology control signal flat LMP. So it does.
I wouldn't say that. Yeah, I would
No?
put it in a double track. So we're looking to provide a more efficient dispatch, which
Yeah.
may or may not lead to. Sometimes you cannot completely levelize the LFP, and sometimes when you change the topology, you may increase. It's unlikely, but we have seen situations in which you increase the congestion rate while you reduce the cost of congestion.
Reduce the cost, and that would be also one of the goals for your planning, transmission planning as well.
Yes.
Does that imply that the planners can do like a great job when they clear those transmission lines, or like how?
That's what I was thinking. Find out who screwed up.
Yeah, what do you do? Yeah.
So when you plan with very limited data. There's a lot of uncertainty. And most of the planning is done on a few snapshots under, let's say, system peak to be anticipated 10 years. But then you need to operate the system 24/7 with a completely different resource mix that shows up. So I wouldn't say that the transmission planners didn't do a good job. I would say that they put into the system enough redundancy that we can exploit. And not exploiting it is not good.
Let me follow up on that. I was down as we were discussing visiting SPP on Friday, and I was talking to Jay Casperry, and Jay showed me a map of SPP from 1971, and a lot of those lines were on there and they're still there. So as you plan the system, you're building it over decades, many decades sometimes. When I was at Madison Gas and Electric, we had a switching situation that we regularly did. We put in a new 138 kV line in parallel with an existing 69, and we used the 69 until it overloaded, then we switched it out. And that's just because of the new line, the old line couldn't handle it. So you just had a switching procedure and it's fine.
And that's a typical example.
Yeah.
Opening a lower voltage facility in parallel with higher voltage.
And I did way back a study with TVA where we dispatched their system, and the only way we could manage some of their contingencies were just to open lines up when they were overloaded, and that fixed it.
Very good.
Thank you.
Thank you.
Yeah.
Time.